This video is a replacement video for the HMM learning and inference video that was broken last Thursday. So initially we talked about different use cases for HMMs. Generally we're looking at three different use cases. In the first use case, we're trying to recover the best path of hidden states x1 to xn given an input sequence y1 to yn. This is typically used when the hidden states have some sort of meaning. For instance, when we were trying to recover language, say the text of something that has been garbled, the hidden state has meaning of the letters, or rather each X state has a letter associated with it. And so you're trying to actually recover those letters. The second most common, or the second common use case is to calculate the most likely path through the HMM, ignoring the actual path that was taken. We just really want the probability of the most likely path. This is used typically when the the hidden states are composed of sort of abstract states. There's just some S number of abstract states. They don't have a real world meaning. This is often used for things like speech recognition, where there is no associated meaning with the X. It's just a mechanism to allow the HMMs to match the input sequence. Then the third common use case is to sample from the HMM. So get a path, either a set of y1 to yn's or a set of hidden states, giving the distributional parameters of the HMM. We won't talk much about that. The example I've given in the past is, for instance, trying to synthesize some dance moves. So you would create an HMM that would have the kinematics of somebody dancing, and then you could regenerate a new movement from that HMM. So last week we talked a little bit about doing inference on HMMs. We do inference on HMMs using dynamic programming. The nice thing about dynamic programming is it is polynomial time, and as opposed to trying every possible combination of a path, you can work backwards from the end to the beginning, figuring out the best path at each step in time, and then going further and further towards the beginning to calculate this recursively. So we use a trellis to illustrate the dynamic program. In this diagram, each one of these columns is a step in time, and then each of the circles is a state of X. So at each step in time, you have the possibility of being in one of the various states. Either, in this case, x is equal to 1, x is equal to 2, x is equal to 3. The nodes have a value associated with them, and that is the probability of y at that time given the x is in a certain state. So for instance, in this node right there, that's the probability of y2, the observed y2, given that x2 is equal to 1. Over here, this state, this node would have the cost of y3 given that x3 was equal to 3. The edges also have meaning. That is the probability of moving from one state to another over time. So for example, this edge is the probability of going from x2 equal to 1 to x3 equal to 1. This node down here would be the probability of moving from x equal to 3 at time 1 to x equal to 2 at time 2. So the way that we do inference on this trellis is we start at the end and we figure out the best path leaving a node. And then given those best paths, we go backwards in time, and for this node we find the best path leaving this, given that we know the best paths leaving the at the following time. And you can just work recursively. So you really are going to calculate two things. First, you're going to have the best path leaving the node, meaning that if there's multiple paths leaving the node, you're going to choose a single one, which is the best path for that node. And then you have what's called the go-to cost, which is for each path leaving the node, what would be the cost of taking that path and then following the best path from then on. So the best path leaving a node is just the minimum of the go-to costs, or sorry, the cost to goes. So we have the formulas down here. The best path leaving a node is just equal to the minimum of the cost to go. The cost to go is going to be the cost of taking a path plus the cost of going through the destination node plus the best cost to go. So for instance, if we were taking a path from this node to this node, the cost of that path would be this probability right here, plus the probability, the cost of arriving at that node, plus the cost to go of leaving that node, which is going to be either the best path of leaving that node, which will either be this path or this path, depending on what the previous calculation is. So we can represent this in a probability. We're going to write, well, first of all, the best path of leaving the node is going to be indicated by CWJ. So W stands for the time, J is the current state, and then C is the best cost. So the cost to go path, this is not the CWJ, this is just the cost to go, again, is the cost of taking the edge, the cost of arriving at the node, and the best cost to go from then on. Note that we're using the negative log probabilities here. So this is the negative log, and then the best path is also the negative log, so you add that instead of subtracting it. So now if we look at the best path leaving the node that we're calling CW, so C at time W of being in node J is equal to the minimum over all possible states of taking a path, arriving somewhere, and then following the optimal path after that. So this is the formula that we recursively apply, starting at the end and moving back towards the beginning. There is a similar formula, which is B of W, which I haven't written here, which is just the best path to actually take. This will calculate the best cost of leaving. And then if you want to recover the path, you basically have to keep track of which path was taken at each step. So essentially what this U was at each step. And so there's a similar set of equations that are actually BW that just indicate which path was taken instead of the cost that was taken. So that was just a brief recap of the inference on HMMs. Now what we haven't talked about so far is how to learn the parameters of an HMM. So if we talk about the parameters that we need to learn, first of all we need to know the number of states. We're going to call that S in this when we talk about our HMM parameters here. It's a number of states, it's a chosen number. It's either based on the thing we're trying to model. For example, for modeling language, we might have a state for every letter plus a state for space, maybe some for punctuation. So S would be determined by that. In the case of, say, speech recognition, we just have to choose some arbitrary S and then probably use cross-validation to determine if it's a good S or a bad S. We also need to know the number of emissions that Y can take or that Y can emit. Remember that we're talking about discrete HMMs here, so Y is going to have some discrete output of states. We're just going to call the number of states that are output T, Again, HMMs can be extended to having emissions that are not discrete, that follow some other parameterization. Remember, we're just using probabilities here, so we can calculate all these things for anything that has a probability distribution. But for simplicity, we are just going to consider the discrete state. So given that we knew the number of hidden states and the number of emissions, we need to find the what we're going to call pi. This is just the probability of starting in a specific hidden state. So this is the probability that x1 is equal to k. And that's going to be an S by 1 matrix. Then there's the probability of transitioning from state I to state j at any given time. So this is the the probability of hidden transitions. So I apologize for this being a little garbled here, but this is basically the probability of x at time t plus 1 equal to j, given that we were at I at x of t. This is going to be a S by S matrix. And then the final thing we need to know is the emission probabilities. So Pj is the probability of emitting a state y, given that you're in a hidden state j. So it's the probability of yt equal to some y value specified there, given that xt is equal to the j here. And that's a T by S matrix. So if we know these three things, we have a fully defined HMM. And then we can do inference on them. So there's two approaches that we're going to look at for determining these kind of numbers. The first one is if we have meaningful states of X, meaning that we're remodeling letters, and we have some corpus which defines the transitions between X's. So for example, if we had a set of text, let's say the book, the text of the book, and we were trying to model language, we could just count up the transitions between various letters. That will give you the Pij and the Pi k. What that won't give you is the Pj, which is how things are emitted. Now, if we need to know that, we can, in the first approach, if we had a known emission process, we can just use that known emission process for that. Now, what do I mean by known emission process? In the example in the book where we garbled text, basically the emission process was when you were in state X, meaning it was associated with a letter, you would emit that same state with probability P, or with probability 1 minus P, you emit either a letter before or after. So because we knew that emission process, we can figure out the Pj probabilities for each of the states. So if we know these three things, or if we had a bunch of pairs of sequences where we had the x1 to xn and y1 to yn, if we had a bunch of those pairs, we could recreate all the needed probability distributions just by using inspection, which just means we're going to count up all of the different transitions, all of the different emissions, and we're going to build the probability up from there. So really, we're just going to count how things happened in our example data or in our known corpus in order to build up the HMM. That is by far the easiest way to do learning, to find the parameters of the HMM, but it is not the only way. Let's say instead that we only had sequences of the visible variables. So we had a bunch of sequences that were y1 to yn, and we had k of these sequences. And just for the nomenclature here, y1 to yn, the little one up in here is the sequence index. So we have sequence 1, which happens to have length n1, and we have sequence 2, which happens to have length n2, up to sequence k, which happens to have length of nk. So each of these sequences can be a different length. What we don't have is the associated x's. So we don't know what the x's are. If we knew the x's, we could use the first approach and just count, but we don't. So what we're going to do is use EM to infer the parameters theta, which is just the pi, pij, and pj that we talked about on the previous page. So EM, that's expectation maximization. We talked about this previously for clustering. What we're going to do is we're going to introduce a hidden variable, which unfortunately is not the hidden variable, not the hidden states x, but a new hidden variable that in EM terminology. And we're going to introduce it such that if we knew it, we could just do the counting, we could just recover the probabilities through counting. So let's look at how that would work. So as we just discussed, if we knew the x's, the hidden states, for any set of y's, any sequence of y's, we could just count all the transitions. But we don't know that. So what we can do is we can introduce a hidden EM variable that we're going to call delta. And that delta is just the setting of, for any given sequence, it's the setting of the possible x values. So here we're going to call it delta t of u I is equal to either 1 or 0. So if it's 1, that means that for this given delta setting, the x at time t was in a specific, had a specific state, and all other ones had a 0. So let's look at the, just to be clear here, t is the time we're talking about, u is the sequence index. We had up here we had k sequences. We're gonna need a delta for each of those k sequences. I is the state index of the hidden state, so it's the hidden state being the state of the x's. So again, what we're looking at is delta is going to take a value of 1 if at time t x for sequence u is equal to state I, and 0 otherwise. And so basically we're going to have, there's all sorts of different deltas, sets of deltas that could be assigned. So when we do EM, what we do is we take an expectation over all possible delta settings. So basically we conceptually iterate over all possible settings of delta, all possible output paths, x1 to xn for every sequence. We take the expectation over all of them, and we iteratively improve our theta. This is very similar to the way that we iteratively improved our clusters back when we were looking at mixture models for clustering, where we would assume we knew what cluster things were. The deltas indicated what cluster we're in, and then we take an expectation over all those possible cluster settings to improve our theta over time. So when we do EM, for HMM, this is actually HMM learning, not inference. When we do HMM, we have to have a Q function, and then we have to maximize that Q function. So the Q function is just, as I said, the expectation over all possible deltas given the Y sequences and the current theta estimate at time n of the negative log probability of those that delta, which means the X states, and the Y settings given a theta. This theta is the free variable here, theta, whereas this is the current setting of the theta at time n. So once we have the Q function, this is called the expectation step, then we can do the maximization step, where we take theta hat n plus 1, at time n plus 1, is equal to the optimal theta, the best theta, argmin of theta of the Q function theta hat at time n. So this looks like a very intractable problem in this form. There are an exponential number of deltas, delta settings. So delta, remember, is the settings. Any given set of deltas is the all of the various sequences of hidden variables for a given y sequence. So there's an exponential number of these. So doing this in the naive way would end up with a very difficult maximization here. However, there is a nice closed form solution. Just like clustering, when you push through all the math, you do all the you substitute in a bunch of the probability, the definitions of the actual probability distributions. It falls out that you get a fairly nice closed form solution. It's still expensive, but it is not exponential. I'm not going to write the closed form solution here. It's available on page 312 of the text. And so if you want to look at it, you can look at it there. Learning in HMMs using EM is probably not something most people will write. You will use a library. But if you needed to write it, it is fairly straightforward, if a little bit messy with all the different indices that